What's going on, everybody? It's High Peak Education coming back at you with another lecture, and this time about universal gravitation and planetary orbits. I'd like to discuss the fact that gravity and orbits relate to things we've already studied in this course, namely forces and things like circular motion. So let's go ahead and get started. Let's first talk about this so-called universal force of gravity. By the way, we will only be taking the Newtonian perspective in this chapter and in this course, not the Einstein perspective, the real modern perspective. So we'll just be taking the classical perspective on gravity. Gravity is actually one of the four fundamental forces of nature. The other three are the strong force, the weak force, and the electromagnetic force. Now, gravity is the most important force on the large scales when the masses are very large, so literally astronomical in size. I mean that figuratively and literally. Astronomical in that they're what you'd study in astronomy class, but astronomical meaning just very large masses. So, what is Newton's law of gravitation? It says for any two masses, call them little m and big M. So some little mass and some large mass. By the way, these are sometimes called mass 1 and mass 2, really just a matter of labeling. Suppose they are a distance r away from each other's center of mass. So here to here is the distance between each other's center of mass. This is the equation we get, that the universal gravitational force is equal to big G times little m times big M over r squared. And this is the magnitude of the gravitational force. Now notice, the gravitational force is proportional to each mass, so the more mass you have, the greater the gravitational force. And it doesn't matter which mass is larger, you still get a larger gravitational force. But it's inversely proportional to the square of the radius. We'll get to that. And notice, to get all the units and the values to work out, we have to use this capital G. Now, capital G is called the universal gravitational constant. It's a fundamental constant of nature, and this big G is actually quite a small number, because when these masses are typical masses, say just a few kilograms, multiplying by this G gives you a very small number of newtons. So notice that the universal gravitational constant in SI units is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Notice that two 1 kilogram apples separated by 1 meter on Earth would only have about 6.67% of a billionth of a Newton force between each other. That's extremely small. Notice that objects must be very large masses, very large scales, in order for gravity to be quite important. So let's discuss this universal force of gravity in more detail, but this time from the vector perspective. From the vector perspective, the vectorial expression for universal gravity is given by this. F vector 1, 2 is equal to negative G m1 m2 over r squared in the r1 2 hat direction. Now let's break this down. First of all, F vector 1, 2 is going to be the force on mass 2 coming from mass 1. So you might call this force 1 on 2. Secondly, notice that it's proportional again to this gravitational constant, the product of the masses, inversely proportional to the square of the distance between their centers of mass. Now it's a minus sign. Why a minus sign? Because it's an attractive force. So what that means is the force is towards mass 1. That is the force on mass 2. Furthermore, let's look at this R12 hat. Now, by the way, this hat notation, you should become familiar with that. Anytime you see that little hat, or sometimes called the caret notation, that pretty much always in math and science means unit, means has length 1. So this is a unit vector. So this R12 vector says nothing about magnitude. It only tells us about direction. In fact, if you left that off, this expression would only be a scalar expression, not a vector expression. So R12 hat is a vector of length 1 that points from the center of mass 1 toward the center of mass 2. In other words, it defines the radial axis, linear line direction, between the center of mass 1 and the center of mass 2. Notice, in other words, it's not necessarily an x-axis or a y-axis vector. So if these masses were along, let's say, an x-axis, you could replace this with the traditional I hat, so the unit vector in the x direction. But in general, we have to write R12 vector, which again goes from 1 towards 2. Okay, now by Newton's third law, what do we note about these two forces? They're equal in magnitude, opposite in direction, so F vector 2, 1 is equal to negative F vector 1, 2. So equal size, opposite direction. For an extended spherical mass, for example, let's say a planet, the gravitational force outside the object is the same as if all the mass were concentrated at the center. This is the whole notion of a center of mass. Now, by the way, if you're on the interior of a planet, the gravitational force is not going to be some constant value, nor can you think of it as all being at the center. It turns out that actually requires some level of integration, and that's beyond the scope of today's lecture. But suffice it to say, you have to sort of perform an integration of how much mass is below you at your current radius and how much is out there above you. Okay, so that's kind of the idea. And then, what's the force of gravity on an object at Earth's surface? Well, if you want that magnitude, use the universal gravitational force equation, and you should be able to plug in. So why does a 1 kilogram apple weigh 9.8 newtons? Because if you plug in 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared for capital G, if you plug in 1 kilogram for the little mass of the apple, if you plug in 5.98 times 10 to the 24th kilograms for the mass of the Earth, and then if you plug in the radius of the Earth, now that should be in meters, that should be 6.371 times 10 to the 6th meters, and you square it. When you work all that out, you should get about 9.8 newtons. That's the force on a 1 kilogram mass. Okay, so you get the idea. Now what about that 1 over d squared, or that 1 over r squared dependence for the universal gravity equation? This is often called the inverse square law, and I'd like to spend some time understanding why this is so important. Universal gravity obeys the inverse square law with respect to distance from the center of mass. Now it turns out many physics quantities also obey this law. Okay? So any physics quantity that can be thought of as sort of a point source of either energy or a point source of energy sort of streaming out can be thought of as obeying the inverse square law. Let's think about why that is. If an object is having all of its energy sort of concentrated at some point, it should have some spherical symmetry. In other words, as the radius increases, the concentration of that energy decreases, but the actual energy on any of those spheres is the same. It's just that on any square patch of area on that sphere, the concentration should be less. So imagine we're on the outside of the Earth. You could imagine that the force of gravity, let's say, on a 1 kilogram apple is about 9.8 newtons for the force, I should say. Now let's just go ahead and round that to 10 newtons, just for the sake of today's discussion. If I go to 2 Earth radii, that is 1 Earth radius further away from the Earth's surface, we have now a larger sphere. Now, what is the radius of that larger sphere? Well, we know that the formula for the surface area of a sphere is 4 pi r squared. We learned that equation back in geometry. If the radius has doubled, there's a radius squared factor there. So a doubling of the radius should be 4 times the surface area. So if the surface area of the new sphere is 4 times, the concentration of energy, in some sense gravity effects, if you will, on that sphere should be 1/4 as much. And as a result, notice that the gravity force will be only 25% of its original value. Notice that if you were at 3 Earth radii from the center of the Earth as opposed to 1 Earth radii, you should be at 1/9 the gravity force, because it's 1 over radius squared, because again, you have 9 times the surface area. Okay? And this just continues. 4 times as far away, 1/16, and so on. Now, I've answered these questions: twice the distance away, 4 times the distance away, etc. So, here's one way to think about the spreading out of that gravity force, just like other quantities that obey the inverse square law. Imagine you have a can of spray paint that sprays horizontally and vertically. Notice that here's 1 area unit, and it's sort of 1 layer of paint thick. But notice that if you take that same paint can and you keep spraying it, and it spreads out horizontally and vertically, you can imagine that the same amount of paint is going to get spread over not 1 square, but over 4 squares, if the distance is 2 times as far away, 2 units of distance. So notice that now it's only 1/4 the thickness. If this is 9 area units, that's what you could fill in here, this would be 1/9 layer thick. If this is 16 area units, 1/16 an area layer thick, and so on. And that's because we're at, say, 1 meter, 2 meters, 3 meters, or 4 meters, respectively. So this is how the inverse square law works. Now, what are those other physics quantities that could obey this? So think about this. Other physics quantities that are field forces. So field forces are forces that don't require contact. Now, the gravity force is a field force. Notice that it's the only field force we really focus on in a Physics 1 class. You know, when we drop something, we drop anything towards the surface of the Earth does not need to be touching that object. It acts through empty space. So gravity is a field force. What are other field forces? Well, the other one that I can really for sure think of would be the electrostatic force. The electrostatic force, or the electromagnetic force, I should say, electricity and magnetism both can operate through empty space. And as a result, they also obey the inverse square law. In other words, if you go, say, 2 units of distance away from a charged particle as opposed to 1 distance away, you'll only experience 1/4 of the electrostatic force. If you're 2 units away from a magnet pole as opposed to 1 meter of distance away, you should be only at 1/4 the magnetic field strength, and so on and so forth. Now, there are other physics quantities you can think of like this, especially things that spread out as point sources of waves. The 2 that really come to mind for me would be sound intensity and light intensity. Sound intensity also obeys the inverse square law. As you spread out sound, notice that if you're twice as far away from a sound source than you originally were, you should only hear 1/4 of the sound intensity. If you're 3 meters away, 1/9, and so on. Same with light intensity. Light intensity, say like a light bulb, it spreads out in concentric circles. So light intensity has a very similar behavior. Okay, so just understand that this inverse square law, you will see this many times in your life. So be aware of it, learn it, and understand it. Alright, so on we go. Let's talk more about gravitational fields. What exactly is a gravitational field? We've already said gravity is a field force, but generally when we talk about the gravitational field, we're talking about the acceleration vectors that surround a mass. The gravitational field from an object of mass capital M on a test mass of little m is defined as the gravitational force on little m divided by little m, and you get this gravity acceleration vector. So notice it's just minus g big M over r squared in the r hat direction. Now consider that a gravitational field is going to be basically the acceleration vectors that surround a mass. Now even though sort of 8 lines are shown here that are all radially inward towards this mass, this is like a field. Think of a field like a field of grass. You could, look at little pieces of grass everywhere, so we could look at these little vectors pointing inward everywhere. Notice the length of these vectors gets longer as you get closer towards the center. So what that means is the gravity force gets stronger as the radius gets less. Now, by the way, a vector field is actually just vectors everywhere in space that surround an object. They have magnitude and direction sort of everywhere in space surrounding. Okay? So there's really sort of 4 parts to it, if you will, here, if you're in 2 dimensions. There's the 2-dimensional point, like the xy coordinate, and then there's the 2-dimensional vector components, the x and y components of that vector corresponding to that point in space. Now keep in mind, here we're drawing this in the plane. Otherwise, it could be 2 triplets, some point in x, y, z space, and then some corresponding vector components in the I hat, j hat, and k hat directions. So that's what this gravitational field vector is really telling us. Now, the field shows vector strength and direction at each point, and since the acceleration is f divided by m, then the magnitude of g vector is the acceleration due to gravity from that object. Now, let's suppose you're on a planet, or for that matter, some moon. The acceleration due to gravity, let's say on that planet or on that moon, is going to be the universal gravitational constant times the mass of that planet or moon divided by the radius of that planet or moon squared. Notice that this just comes right out of Newton's universal gravitation equation. Now suppose you plug in the values for Earth. I already mentioned those values for Earth earlier in the lecture. You plug those values in here, including the gravitation constant, you get 9.8 meters per second squared. That's where that number comes from. Now suppose we perform this for the moon. Notice the moon is about 100 times or so less massive than the Earth, and it also has a about 5 times smaller radius. Okay, so if you plug those values in, you should have about 1.6 meters per second squared. That is, the gravitational acceleration on the moon is about 1/6 of that of Earth. Okay, so when you jump on the moon, you can jump much higher and you're much slower to descend to the moon's surface. What about ocean tides? Well, ocean tides are affected by Earth's gravity. They're strongly affected by Earth's gravity and also the moon and the sun gravity. Okay, so notice that this is sort of what low tide looks like, and this is sort of what high tide looks like. You can have dramatic differences depending upon the geometry of the ocean or bay, basin, that sort of thing. Tides tend to happen about every 6 hours on average. There's lots of variation given other factors. And the reason tides go as they do is that you can think of the Earth's oceans as sort of a jello type substance. I mean, oceans are a fluid, so they're free to flow. So it turns out that the side of the ocean that faces the moon bulges out, but then the side of the Earth's oceans that faces away from the moon also bulges out. So I would say these locations and these locations that are on opposite sides of the Earth from each other are both experiencing high tide, but the sides that are perpendicular from the moon are experiencing low tide. And by the way, you can also have higher than normal high tides when you have spring tides, and that's because the moon and the sun are basically in alignment. But you can have lower than normal high tides if you have neap tides, and again, that's when the moon and the sun are sort of perpendicular to one another. Okay, I will perform this gravity force calculation example in a later video, and the same with this example. Okay, so these are both going to be examples of calculating with the universal force of gravity and then also getting a little bit into orbits with circular motion. So now let's talk about planetary orbits around the sun. It was Johannes Kepler that analyzed planetary motions and developed a set of empirical laws for their orbits. Now these empirical laws are geometric, and Sir Isaac Newton was able to come along and verify these mathematically and using calculus. Now Kepler was inspired by, I think in America we usually say Tycho Brahe. I think he's Danish. I think it's pronounced Tycho Brahe. So I'm doing my best. Those of you who know how to pronounce this name, you can tell me in the comments. Later, Newton came along and again confirmed the geometric considerations with mathematical calculations. So these are now known to us today as Kepler's laws of planetary motion. So it was long assumed that planetary orbits had to be circular. But Kepler found, based upon these observations, that the orbits could not be explained as perfect circles. He showed that actual ellipses could successfully explain the motion. So let's think about an ellipse. Okay, how do you construct an ellipse? Well, you usually put down 2 push pins and a piece of string, and what you do is you preserve the distance between those 2 push pins, and the distance between each push pin and the pencil, the sum of those distances is preserved. So the set of all points that is equally distant from 2 points in space is an ellipse, okay? At least in the plane. By the way, notice that we usually draw a line between those 2 points in space that we have total distance from preserved. Each of those special points is called a focus. The plural is called foci. And that line between the foci and hitting the ellipse is called the major axis. Half of the major axis is called the semi-major axis. The minor axis is perpendicular to the major axis, and the semi-minor axis is half the minor axis. Notice the semi-major axis we call A, the semi-minor axis we call B, and the distance from the center to a focus we call C. Now, let's see. Notice the length of the major axis is 2A, the length of the minor axis is 2B. So by the way, I hope you've seen these equations before. It's in like a pre-calculus or a college algebra class. By the way, notice that this ellipse right here is what we call x-axis major. That is, its major axis is elongated along the x-axis. Whereas you could have an ellipse that goes this way, and that would be y-axis major. So each one is possible. Now, ellipses have different elongations. Notice that if you have no elongation, it's a perfect circle. If you have an elongation that makes it more like an oval of 0.5, notice the foci are stretched out from each other. Here's an even greater elongation and a very great elongation. So this elongation is what we often call the eccentricity, which is usually given the symbol lowercase e, and it's the unitless number that indicates how elongated the ellipse is. A small e is very round, a large e is very elongated. Now e for the eccentricity is c divided by a. Notice that as long as you keep the length of the major axis the same, which each of these ellipses is keeping, but if you stretch out the distance between the foci, then c is increasing and the ellipse is getting more elongated. So we find that the two extreme possibilities for eccentricity is e equals 0 for a circle, that's the round limit, and e equals 1 for a straight line, that's the elongated limit. Now let's talk about Kepler's laws of planetary motion. So the first law is that the orbit of a planet around the Sun is an ellipse, with the Sun at one focus of the ellipse. Now there's nothing at the other focus, but the Sun is at one focus. Now by the way, when you're closest to the Sun with the planetary motion, we give that the name perihelion. So helios, like being the Greek word for sun, and then aphelion is when you're furthest from the Sun. Okay, so those are the near side and the far side of the major axis. Now, let's talk about these eccentricities. So Venus is very nearly circular, 0.007, almost a perfect circle, whereas Pluto is much closer to 0.25 or so for its eccentricity. So it's a very elliptical orbit. Okay. Now, by the way, also comets have highly elliptical orbits, even more elliptical than Pluto. Okay. Notice that here's Halley's Comet. Notice that Halley's Comet has an eccentricity of over 0.95. That is to say, it's moving in a very, very elongated orbit, which is very narrow and has its foci very stretched out. How about Kepler's second law? Kepler's second law tells us a line joining a planet and the Sun sweeps out equal areas in equal time intervals, sometimes called the law of equal areas. Now, here's the idea. Notice that when the object is close to the Sun, near perihelion, the object, let's say in 30 days, sweeps out a large angular change, but it's at a small radius. But notice that when the object's near aphelion, in 30 days, it sweeps out a small angle, but it has a large radius, so this area and this area, both of the blue areas, are in fact the same. Now that's a geometric interpretation. Now when you consider forces, objects move fastest at perihelion and slowest at aphelion. Let's think about why that is. At perihelion, the radius, that is between the center of the planet and the center of the Sun, is smallest. So the gravity force is greatest. Well, if the gravity force is greatest, I think the centripetal force is greatest. And that means the velocity should be greatest. So we travel fastest at perihelion. Another way to think about this is that you move faster so as to not crash into the Sun at perihelion. At aphelion, the planet does not move as fast because the radius between the center of the Sun and the planet is larger, and if the radius is larger, the gravitational force is less, so the centripetal force is less, and as a result, the velocity is less, and the object does not need to move so fast to prevent crashing into the Sun. Now, by the way, this is sometimes called the slingshot effect, that planets sort of slingshot around the sun, move faster in this region and slower out here. And it can be shown using Newton's laws and the rotation from this class that Kepler's second law, equal areas, equal times, follows from the conservation of angular momentum and the conservation of mechanical energy. So if you consider those, you can just basically write down why equal areas and equal times should be correct. What is Kepler's third law? Now, Kepler's third law is an interesting one, and it tells us how orbits are related to one another. And that is, a planet's orbital period squared is proportional to the distance from the sun cubed. Now, it's proportional through various geometric constants, including pi, so that Kepler's third law, in its equation form, is given by this. The period squared is proportional to the distance from the sun cubed. Now, for the distance from the sun cubed, we often just use the semi-major axis. It turns out the semi-major axis, which is, again, half of the major axis, is sort of a good average distance away from the sun, basically. And it's not so much an average as it is sort of a characteristic length scale. Now, what is the proportionality constant? Well, believe it or not, the proportionality constant is going to be 4 pi squared divided by the gravitation constant and the mass of the object you orbit around, in this case, the sun. Okay? Now, by the way, this actually comes out of basically the orbit velocity equation, which I will show in a later video calculation, and the fact that 2 pi is part of the equations of converting angular velocity to period. Okay, so there we go. So I will perform this example of Kepler's third law also in a later video. The last major thing I want to discuss with respect to gravity and orbits is the energy perspective, namely mechanical energy, and the fact that we have this notion of bounded orbits. So what is a bounded orbit? The idea is that in an orbit, a planet, or for that matter, even like a satellite, is not free to transfer its own energy. In other words, it can't just freely do work, so to say. So because the mechanical energy is bounded, the way we define the gravitational potential energy is a little bit strange. So let's go ahead and see what that would look like. Since forces can be defined in terms of their potential function, the gravitational force can be written in the following way. Fr is equal to du dr. Now let's think about where that comes from. If you recall back into the energy chapters, the way we were able to show that force is related to potential function is you take the minus gradient of the potential function. Typically we called this F was equal to minus du dx. Say like capital U was the elastic potential energy and x was like the distance left or right for a mass on a spring. Thus, the universal gravitational potential energy for two masses is given by an equation I'm going to show here in just a second. Now you can show that this equation is true by integration. Okay, so if we integrate both sides of this equation with respect to r and take a minus sign, and for F we put in the radial force. Well, the radial force is just the universal gravitational force, and that's big G, little m, big M over r squared. And we integrate both sides. Now we integrate both sides, the G and the masses are constant. So it's basically integrating we're integrating r to the negative 2 dr. Now that's very similar to a calculus 1 integral of x to the minus 2 dx. So when you integrate that, you get 1 over x, in this case 1 over r, with also a minus sign. So you get this expression, that the universal gravitational potential energy is minus g m1 m2 over r. Now, first things first, why is it negative? Notice that, first of all, it's still proportional to g m1 and m2, but now it's not inverse square law, it's just inversely proportional to r. But it's negative. Now let's think about why that is. When two objects are separated out in the universe and they're very far from each other, we say that the gravitational potential energy, by definition, is zero. Now before, earlier in the class, I said you can set the zero value for the potential energy. You are free to choose where it is. However, in this case, someone is just telling you where it is. It's when the objects don't interact. When they're very far away, the gravitational potential energy should be zero, because they're not interacting via gravity. Now, when objects come closer to each other, via the conservation of mechanical energy, I think that the objects should accelerate towards each other via Newton's law of gravity. So the kinetic energy should go up. But if the kinetic energy goes up and the potential energy started at zero, the only way to conserve the mechanical energy is that if the potential energy goes down and it becomes negative. So that's one justification why this is negative. Another way to think about why it's negative is because, well, the calculus tells us that by integration there's a minus. And sort of the last and maybe most compelling way to think about this gravitational potential energy being negative is that these objects are in bounded orbits. Because they're bound, their potential energy is negative. They can't just sort of realize energy on their own. They have this sort of constrained energy. So for a mass little m orbiting around a much larger mass capital M, so that big M is much, much larger than little m. So imagine the big mass is stationary. This is the mechanical energy equation. The mechanical energy is the linear kinetic energy plus the universal gravitational potential energy. So 1/2 mv squared minus g little m big M over r. Notice what the graph should look like of energy, that is total energy, versus radius. Notice if something is unbound, in other words, if it's not constrained by some gravitational field or something, its total energy is positive. In other words, it can freely do work and so on, things like that. But if something is bound, when its radius is at infinity, its energy, as far as interacting with the other object, is zero. But when it gets closer to the other object, its total energy becomes negative, and for that matter, its potential energy also becomes negative. So notice that as r decreases, think about this, as r decreases, then you have a larger fraction here. But if you have a larger fraction with a minus, it becomes more and more negative. In fact, this actually approaches negative infinity when the objects are sort of, infinitely close, so to say. So this is kind of theoretical, but you hopefully get the idea. Now, the total energy constant can be found if the system is either circular or elliptical. And see my previous textbooks. Now, a couple things to say about this. First of all, in order to find that, suppose it's a circular orbit. If it's a circular orbit, what you would do is you would insert the equation for the orbit velocity. So the orbit velocity, v, is equal to square root of gm divided by r. Okay? And that's derived in another example video. And when you do that, when you plug in square root of gm over r, and you square it, and then you work all this out, you get that the total energy in a circular orbit is just going to be half of the potential energy, at least in terms of magnitude. Now, what if it's in an elliptical orbit? Well, in an elliptical orbit, the orbit velocity is going to be just the exact same expression, except everywhere you see a radius, you put in the semi-major axis. You put in lowercase a. So if you're in circular orbit, the total energy is minus g little m big M over 2r. If you're in an elliptical orbit, you get minus g, little m big M over 2a, and a being the length of the semi-major axis. So notice it kind of works out all really nice here. Now let's talk about these energy equations for an interesting application. What if we're launching things away from the surface of a planet? Well, if we do that, what we're trying to do is we're trying to break free from the fact that it's bound. In other words, we're trying to break free from this potential energy, knowing that if we put in enough kinetic energy, we can become unbound. So that's the idea. We want to sort of become unbound. So suppose at first you try to throw an object from the surface of the Earth, which is at the radius RE, to a height R max. And R max is radius of the Earth plus some height h above the surface. Now, by the way, let's assume that you're throwing the object high enough that it's going to come back to the Earth, but it's thrown high enough that the gravity force depends upon radius. Since the total energy is conserved, initial kinetic energy is equal to the gravitational potential energy final, and gives the relationship between V initial and R max. By the way, this is the universal gravitational potential energy. So that should be the following. So the equation is V initial squared is equal to 2g mass of the Earth times 1 over radius of the Earth minus 1 over R max. And R max is the maximum distance from the center of the Earth, and R max is the same thing as radius of the Earth plus h, and h is the height above the ground. Now, how would you get the so-called escape velocity? What's the whole idea of escape velocity? You want to throw this object fast enough, sort of hard enough, that it never comes back. In other words, the potential energy just goes to zero, but the kinetic energy is large enough to overwhelm the potential energy. And in fact, this R max goes to infinity. So if you take this equation and let R max approach infinity, you should get the equation for the escape velocity. Now when R max goes to infinity here, you have 1 over infinity, which is like 0. So you have 2g me over re, that's the radius of the Earth, and you take the square root. And you should get this equation. That's exactly what I said. 2 times gravitational constant times the mass you're trying to escape from, in this case it's Earth, over the radius of the thing you're trying to escape from. Interestingly enough, the escape velocity does not depend upon the mass of the thing that's trying to escape. It actually cancels out from the equation, so little m goes away. But indeed, do you need more force to push a larger payload mass into the orbit and escape it from Earth? Well, sure you do. But that's just because an object that has a greater mass has a larger gravitational force. But in either case, as long as you can build up to this escape velocity, theoretically you can escape from that thing's gravitational field. Now, by the way, again, like I said, it doesn't depend upon mass. Okay? But as an object gets more massive, it's proportional to the square root of that mass, but inversely proportional to the square root of the radius. So I will work on this gravitational energies example also in a later video. Lastly, I want to briefly discuss my limited knowledge but an interesting topic of black holes. What is a black hole? It's an object where all the mass is concentrated at a singular point, which we call a singularity. It is black because even no light can escape. In other words, the escape velocity is greater than the speed of light itself. Now, the surface where the escape velocity equals to the speed of light is what we call the event horizon of the black hole. Okay? And then RS, this radius from the center of the black hole to the event horizon, is what we often call the Schwarzschild radius. And the Schwarzschild radius is 2 times the gravitational constant times the mass of the black hole over the speed of light squared. Okay? And again, this can sort of be derived from energy considerations and things like that. By the way, notice that it's not too different than this equation right here. If you square both sides and set the escape velocity to c, speed of light, you can solve for that radius, and it's just the Schwarzschild radius. Okay, so that's kind of where it comes from. Now, what happens when you're very close to a black hole? Well, bad things, man, bad things. Near black holes, the force of gravity changes very quickly with distance from the black hole. This is known as a tidal force. Notice that when your arms are a little further from the black hole, they undergo strong gravity. But your feet, let's say your feet are closer to the black hole, they experience much stronger gravity. So you're stretched vertically and you're squeezed horizontally. So examples of tidal force effects include the sea tides from the moon and the fact that the same side of the moon always faces the Earth. Tidal forces near the event horizon of a black hole are lethal to humans, and this is what we call spaghettification. In other words, we're stretching the thing out. So obviously not pleasant to experience this, as a human. Now, what about types of black holes? So as far as we know, there are 2 types of black holes: collapsed stars and ones at centers of galaxies. Ones that are collapsed stars are about 3 to 50 or so solar masses. And then the ones at centers of galaxies are about 1 million to 1 billion solar masses. The acceleration due to gravity at the event horizon for a black hole of mass m is given by this equation. I'm not going to go through where that comes from, okay? But notice that it's speed of light to the 4th over 4g mass of the black hole. Notice the force of gravity at the event horizon is actually weaker for more massive black holes. Interesting. Now, the last slide I'll show in this lecture is something I hope you have seen before. This is a pretty famous scientific discovery that was only made, just about a year or so before the recording of this video. Namely, the so-called Messier 87, the M87, galaxy has a black hole in it. And it's a very distant galaxy from Earth. And the so-called Event Horizon Telescope, the EHT, was able to take photographs of this black hole signature. Now, by the way, this Event Horizon Telescope was actually multiple telescopes around the Earth. It was like a collaboration of 8 telescopes or 9 telescopes or so from different places in the Earth. And they all had to be looking at the same black hole from different angles at the same time. The images had to be merged together. They had to be synchronized. They had petabytes of data. And then basically, they were able to assemble this famous image and other images. Now notice, the event horizon is here. And then outside the black hole, there's radio waves of radiation passing by the black hole. Previously, black holes couldn't be imaged. We only could surmised that they were there from things like Hawking radiation. That's named after Stephen Hawking, by the way. And yeah, basically, so up till last year, we had really good evidence of black holes in the universe. And in the last few years, we were able to detect gravitational waves, but now we can actually see signatures of black holes. Now, by the way, the Event Horizon telescope team hopes to soon after make animations of these things. So take multiple images and sort of record them together as a movie, so to say, to see how these things evolve in time. So we're living in exciting times now where we're starting to understand these distant objects in the universe. So, all right, so thank you very much for your attention, and thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please share this video amongst your social network to grow the channel. I look forward to reading your comments as well, and I look forward to seeing you in the next video.